Hello and welcome to this presentation on biofilms. The first thing I have to do is apologise for the lack of webcam. We seem to be having a few technical issues with you actually seeing me, but I think as long as you can see the presentation and you can hear me, then that's good enough. And I won't have to worry about pulling funny faces and embarrassing myself as I talk through this presentation. So welcome to everybody. The idea of these presentations, these webinars, is to share some of the information that Vikan as a cleaning company have accumulated over the years, and to share this with the industry in an effort to support them with some of their big challenges. And one of the big challenges that we often come across are biofilms in the food industry. So we thought we'd bring together all the information that we've gathered into this webinar and share it with you in order to support you. So my name is Deb Smith. I'm the Global Hygiene Specialist for Vikan, and I'm going to take you through what biofilms are and then how they can be controlled. So I'm going to start with what biofilms are made of. 98 to 99% of a biofilm is actually water. It's only about 1 to 2% of that biofilm that's made up of microbes. Obviously that's because microbes are very small, so in percentage terms you can still get millions of bacteria even in 1 to 2%. What those microbes are is something that we don't actually know, and something that we're finding out more and more about every day. We do know that they can be a complex mixture of microorganisms that work together to form the biofilm, and that it can include some of the pathogenic or harmful bacteria that we're concerned about. Now, as the biofilm develops, it also starts to consist of this slime. That's obviously the non-technical term. The technical term is the extracellular or exopolymer matrix, and this is made up of polysaccharides, nucleic acids, and glycoproteins. So what's needed for a biofilm to form? Well, we know we need the microbes, we know we need the water. Obviously, then you need a nutrient source for the microbes so that they can grow and develop into the biofilm. You also need a surface on which the bacteria can attach and then form the biofilm. And you need time for the biofilm to develop. And if you have all of those things together, you end up with your mature biofilm. So where can biofilms be found? This presentation is obviously focused on biofilm control within the food industry, but biofilms can be found in almost every surface in nature. The one that you'll probably be most familiar with is the biofilm in your mouth, when the plaque bacteria that are present form overnight to form a plaque bacterial biofilm on your teeth. So they use the moisture and the food and the warmth within your mouth to develop overnight to give you this bacterial biofilm. Another easy to see place for biofilms is in riverbeds. Here they have all the nutrients and water they need, and they're obviously given a lot of time to develop, and they can form very visible biofilms on the rocks in the bed of the river. You can also find biofilms in the food industry, and I have to say that I'm very pleased that I don't see biofilms of this maturity in the food industry very often, but on occasion you will come across them and they can look pretty disgusting. So biofilms in the food industry are there. They're not always this bad, but they are, I can guarantee you, they will always be present somewhere. So how do biofilms form? Well, we now understand that it's a 6-stage process. So there are always free-floating bacteria present in the environment, and eventually some of those free-floating bacteria will settle onto a surface. Given a bit of time, those bacteria will start to clump together and attach to the surface. And then given a bit more time, they start to grow and divide and form the early stages of a biofilm. Given even more time, they reach the mature biofilm form, and here they start to develop this exopolymer matrix to cover them and protect them. As the biofilm matures and ages, a portion of the biofilm then disperses by releasing free floating cells back into the environment, and the biofilm formation cycle repeats itself. And all of this takes time. Now, the time it takes will depend on many things, including the availability of the nutrients for the biofilm, the microbe type within the biofilm, and the temperature that the biofilm is forming in. So determining this time is quite difficult because of all these variables. And this can be very difficult in different food factories that have different nutrient availabilities, different microbial cultures, persistent cultures, and different temperatures. This is a quite neat little video that I came across on YouTube. Actually, I don't think it was YouTube, but anyway, which shows the formation of a bacterial biofilm in sort of an animated form. So I'll just let you watch through this. So as you can see from that short video, many of the things that I've already mentioned were covered in that video, but when we look at the formation of the biofilms again, there were a few things that I haven't mentioned so far. So you'll notice that in the video it talked about a thing called molecular signaling or quorum sensing, where the bacteria are really working very much as a cooperative. They're signaling to each other to optimize their survival within the biofilm. They're releasing chemicals between each other to tell each other about how many there are, what state they're in, and will actually generate changes in their gene regulation, which, as you've seen, lead to things like the formation of pili, which can just further improve the survival of the bacteria within the biofilm. Again, this is an area that we're finding out more and more about every day, especially with some of the great molecular techniques that we have available to us now. So I think this is an area where we will continue to discover more about biofilms, and that might help us in the future determining how we can control them better. So let's have a look at biofilms in the food industry, and I've got this example of a pea processing line to demonstrate the impact that the biofilm can have on product quality as it moves through the factory. So as peas come into this processing unit, they go through a hot water blancher. And the peas travel up the conveyor belt, they move through the hot water blancher, which is actually designed to stop the enzyme activity, but obviously has an impact on the microbial quality too. And if you sample the peas for their microbial quality after they've been through the blancher, they're relatively clean. They then move along the various conveyor belts on their way through to the final point where they are frozen and packed. And if you take a sample of the peas at that point, you'll see that the microbial load on the peas has increased significantly. And the reason for that is down to bacteria that they've picked up along their journey between the blancher and packing. And some of this can be down to biofilms. These biofilms will have developed on the surfaces that they touch, for example here on the conveyor belts, or on the undersides of equipment, or possibly in areas of bad hygienic design where food and bacteria can get trapped for a long period of time, and biofilms can start to develop and then shed their cells back onto the food that passes over them. To investigate how quickly this biofilm formed, these stainless steel plates were placed along the conveyor belt side, and they were taken off at periods of time and stained with an epifluorescent stain to show the coverage of bacteria on each of the slides. And this is the coverage of the biofilm after about 16 hours. The biofilms in the food industry are commonly found in old or poorly designed and or maintained buildings and equipment, including things like drains and pipework. This is probably one of the most common places you'll find biofilms. But you can also find them behind poorly fitted or sealed and damaged wall and door claddings, and on floors, in leaky roof cavities and on damp ceilings, on the undersides of surfaces and in nooks and crannies, and within food processing equipment and cleaning tools. What we don't know is where all of these biofilms are, and some of these biofilms can go undetected for years, and these are often the ones that go to cause us problems. So until we discover them, it's very difficult to actually deal with them. So why are they such a problem within the food production environment? Well, biofilms will aid the microbial transfer, the growth and the survival of the microorganisms within them. So they will help them transfer from the environment to the food contact surfaces, and from the food contact surfaces to the food product. And that transfer can be aided by people, by air, by moisture, equipment and pests. It also makes the microbes within the biofilm much more resistant to the normal control measures that we would employ. So the use of chemicals in terms of cleaning and disinfection, and even physical forms of control like heat and radiation, the biofilm protects the microorganisms within it. And there have been studies to show that microbes in a biofilm can be up to 3,000 times more resistant to disinfecting chemicals than free floating cells. So what happens if it all goes wrong and you have an attack from a biofilm? Well, this was an incident that took place in 2008, so quite a while ago now, but it was such a big outbreak that it made international news. So it happened in Canada, and it resulted in 24 fatalities associated with cooked sliced meats packed by Maple Leaf Foods in Canada. The source of the contamination was tracked to a biofilm within a meat slicing machine. And you can see an example of a meat slicing machine in the bottom corner here. The industrial ones can be even more complicated than this one. So obviously contamination was getting deep within that equipment and causing a problem. The slicing blades of the machine then acted as a transfer mechanism for the bacteria from deep inside the machine onto the sliced meats. The slices were cleaned on a daily basis, which is normal, obviously, within a food factory. But during the full disassembly or a periodic deep clean of the equipment, inside they found a biofilm which contained the listeria that was causing the problem, and this had survived the daily cleaning process. The total cost of the outbreak was estimated at $242 million, and the cost to Maple Leaf Foods at $77 million. So you can see that a biofilm can cause both a devastating impact on the company, both financially and obviously from a brand reputation point of view. The next example is actually one from Denmark, a bit more recent. I included this one because Denmark are obviously the home of Vikan, so it's obviously close to home for us. And it involved this very traditional rolled lamb sausage product called rullepølse, and I've apologise to my Danish colleagues for the pronunciation. This resulted in 41 cases of listeriosis and 17 fatalities. And in a country of 5 million, which is all that Denmark has in terms of population, the impact of this was massive. In fact, it made the national news, who went in and did a sort of a news documentary story. And you can see here an image from that documentary. The source of the contamination was traced back to a biofilm in the production area drain, and water that was poured down the drain then cross-contaminated through splashing and aerosols to the cooked rolled lamb sausage that was handled in the same area. Unfortunately, because this is a very traditional product favoured by the elder population of Denmark, it was served to them, but many of them were in a health impaired condition or in elder homes, and so they were a particularly vulnerable group, which led to the high level of fatalities. So, as I said, we don't always know where we can find biofilms, and we don't know where they will attack next. So we have to be constantly vigilant, both in terms of protection of the business, but also protection of life. So let's look at how we can control biofilms. There are many different methods available to us, some of which I would say are what I would class as more novel control methods. Now, the ones I've listed here range from ones that are already commercially available to ones that are still in the research phase. So things like enzymic detergents and electrolyzed water, even bacteriophages, some of those there are commercially available preparations available to use in the food industry. Others, like the non-thermal atmospheric plasma, are still very much at a research phase. But all of these, I would say, have been shown to work relatively well in a laboratory situation, but the data for them being used in the real world is still relatively limited. There are now some case studies that are coming through, but it is still relatively limited. So I'm not really going to focus on these. What I'm going to focus on are what I would call back to basics. These are the tried and tested methods that we've been using in the food industry for many years, and that I often think get forgotten in place of these more novel methods. But actually, these ones work, and they have worked for a long time. So let's see if we can stick with those initially, and then if new stuff comes along, we could play around with that too. So one of the fundamentals is obviously effective cleaning and disinfection practices. Then I'd also consider hygienic design, good hygienic design, as a fundamental for controlling biofilms, and the regular maintenance and replacement of equipment and facilities is also being key to that control. So we'll start with effective decontamination, and I just wanted to run through a few definitions, as I'm aware that I may have an international audience who sometimes the definitions vary between particularly the US and Europe. So for a European audience, and for me in Great Britain, cleaning is the physical removal of contamination, whether that be microbes or other food safety hazards. And cleaning removes the majority of the contamination, especially in terms of microbes. Disinfection is the use of heat, radiation, or chemicals to reduce the microbial load to an acceptable level. A detergent is a chemical used to aid the physical removal of contaminants, so that's to aid cleaning. And a disinfectant is a chemical that lowers the level of microbial contamination to an acceptable level. You might also hear me use the word sanitizer, which in the European sense means a combined detergent disinfectant chemical. And I've added sterilization in here just to stress that cleaning and disinfection don't actually remove 100% of bacteria. It's only when you go to the sterilization phase where you can assure the destruction of all microorganisms, including spores, usually using something like heat or radiation. So going back to our biofilm model again, let's look at when the most effective point for cleaning biofilms could be. The most effective way to control biofilms is to decontaminate them at a frequency that prevents them reaching their mature phase, bearing in mind that we know that when they do, they can be highly resistant to the chemical disinfectants in particular. So it's about really determining a frequency through monitoring of the biofilm formation and risk assessment that prevents them getting to that mature biofilm stage. So we're looking at a time point, anything before the formation of biofilm and after either the monolayer or the microcolony stage. And how then do we make this decontamination effective? Well, I'm sure many of you are already aware, but it really is a multi-task force approach that utilizes a whole raft of actions, including time, chemicals, and temperature. But it all starts with cleaning. And as I've already mentioned, cleaning removes most of the contamination and makes disinfection more effective. I've picked out some data here from a Camden study, which shows the level of microbes before cleaning, the level of microbes after cleaning, and the level of microbes after cleaning and disinfection. And if you have a look at that microbial reduction in terms of percentage, you can see that the cleaning phase removes nearly over 93% of the microbes, and then the disinfection stage is a further 6.4%, taking the total to 99.8%. So it's the cleaning really that does the majority of the work. Selection of chemicals is incredibly important, and your cleaning chemical supplier is the expert in this area. Go to them for advice on the types, concentrations, temperatures, contact times, health and safety information that they can give you based on your particular environment and your particular challenges. They can also possibly provide you with training and even the equipment to dose and apply the chemicals to your equipment. So they are a very valuable source of information. One thing that I would stress is that the cleaning chemicals must be made up and used as per the cleaning chemical manufacturer's instructions. They spend a lot of time and effort and money developing the formulations and determining these factors in terms of making sure that the chemical works really effectively. So please follow their in-use instructions. Please also make sure you leave the chemicals in contact with the item being cleaned for long enough for it to be effective. This is something I very often see not being done. And also then thoroughly rinse it from the surface after use if that's appropriate for the type of chemical that you're using. So let's look at some of the different cleaning techniques that can be used. The first one is foaming. This is a good decontamination procedure for large areas such as walls and floors, or large pieces of equipment like conveyors and tables in open production equipment. The key factors for foaming involve chemicals and time. So you use a spray nozzle to deliver the chemical foam onto the equipment. This is then left for a period of time to act on the soil and is then rinsed off with the released soil. The mechanical action from foaming comes from the shear forces created by the foam moving slowly down the surface and the bursting of the bubbles in combination with the pressure and action of the rinse water aid to clean the process. Manual cleaning tools can be used additionally for any detail or deep cleaning of equipment. And obviously this is a technique that's only really used in wet cleaning environments. Then there's cleaning in place. This is a commonly used technique to clean pipework and closed vessels. In this case for wet foods as liquid and semi-solid foods in the dairy industry or for sauce production. It utilises chemical, time and temperature predominantly. Aggressive cleaning chemicals, sometimes at high temperatures, are pumped around the system for a period of time. Mechanical action in this case is provided by the turbulent flow rates that are generated by an automated CIP system. And manual cleaning tools are sometimes used for the additional cleaning of the detail or deep cleaning of the valves and sampling ports on these types of system. It again is a predominantly wet cleaning technique, but in dry goods manufacture, there can also be dry cleaning with sugar scrubs or salt scrubs. And then we come to manual cleaning. This is probably the most common method of cleaning used in the food industry. It's really good for decontaminating small to medium-sized production areas and equipment. It's good for deep cleaning and detail cleaning and cleaning of complex equipment. With regard to temperature and chemicals, we have to be a little bit more careful here because we're thinking about the risk to the user. The user is in much more direct contact with the chemicals and the temperatures used when they're manual cleaning, so we need to ensure their safety when this is happening. But the most important factor for manual cleaning is really the time and the mechanical action. So it's only really effective if the staff are trained and given sufficient time and appropriate equipment to conduct the cleaning effectively. Fortunately, the other thing that's great about manual cleaning is that you can use it for wet or dry cleaning. As a manufacturer or as a representative of a manufacturer of cleaning tools, it pains me to tell you that all cleaning activities can spread contamination, but it's unfortunately true. What we're trying to do is really for you to select the cleaning equipment that maximizes, in this case, biofilm removal and minimizes its spread. So we've ranked the different cleaning actions in terms of risk for spread of contamination. And you can see that things like wiping and scraping, scrubbing and sweeping are fairly low to medium risk. But when you start to get to the high pressure hosing end, you're really increasing the risk of spread of contamination by that cleaning action. And really to demonstrate that for you, this is some work that was done by Camden. This is an ex-colleague of mine, Karen, who's using a high pressure hose in a slot train and these strips of paper that are suspended from the ceiling or on these boards to capture the droplets and aerosols that are created when that happens. And using that, we developed this model which shows the spread of contamination when the high pressure hose impacts on the slot train, which is shown by the blue arrow here. You then got the droplet spread, so the droplets are spreading for a distance of 7 meters forward and to a height of about 3.5 to 4 meters. And obviously that means that any biofilm in that slot train, any cells from that will be carried within those droplets and will be able to settle back onto anything within that area that's affected by that spread. So a few tips on how to prevent that cross-contamination happening in a real factory environment. Obviously, firstly, choose the equipment and the method that will minimise that happening in the first place. Don't clean or try to minimise cleaning during production when you've got foods that are open or foods that will be in contact with food contact surfaces. Ideally, well, not ideally actually, but if you can, move things as far away as possible from open product before you clean them, and ideally physically segregate them from areas where the food is being produced by either removing them to separate cleaning rooms or possibly the use of screens to minimize the effect of splashes. Okay, so that now brings us to the hygienic design portion of the presentation, and this is something that I do think is fundamental to good biofilm control. Hygienic design really means the ability to clean something easily, and good hygienic design principles are well-founded, and they include things like no sharp internal angles, the avoidance of areas that are difficult to clean and sanitize, so avoiding nooks and crannies and deep recesses, preferably having things of one-piece construction or that are quickly and easily disassembled and reassembled, which encourages regular cleaning and disinfection. Having a smooth surface finish, a rough surface finish is very difficult to clean. And obviously within the food production environment, having things that are made of appropriate food contact compliant materials. Now, these principles are outlined in the EHEG Guideline 8, which is available for free download from their website. And for any of our American audience, I'm sure that 3A, who are the sister organisation to EHEG in Europe, will have similar guidelines that you can get access to. So why do we have to think about hygienic design, other than, for me, what I think is a common sense approach that it makes things easier to clean? Well, it's becoming more and more important with regard to global food safety standard requirements. And in fact, the new GFSI version 8 will include benchmarking requirements on hygienic design. And if you'd like to find out more about that, you can go to this link and find out more. In fact, at the moment, BRC and FSSC 22000, as two of the largest global food safety standards in the world, do mention hygienically designed, but only specifically in relation to cleaning equipment, which is, I find, quite extraordinary. But I'm sure that with the addition of benchmarking requirements in GFSI version 8, hygienic design is going to be much more common in these global food safety standards. So why the benefits of good hygienic design? Well, we've mentioned a few times that they makes things quicker and easier to clean, but it also minimizes the risk of product cross-contamination, like the one you saw, for example, with the slicing machine for maple leaf foods, and it maximizes food safety and quality. Consequently, it reduces the risk of expensive product rejection or recall. It will minimize food waste, and it has all of the associated cost benefits. So really, there's no good reason not to have hygienic design incorporated into your equipment and facilities. Here's some examples of bad hygienic design that I've come across in my time. So this first one is a slot drain again. These are notoriously difficult to clean because they are so narrow and you need just the right product to get into them. And obviously drains are a perfect place for biofilms to form. The floor around this drain has also either been poorly installed or, I think more likely through wear and tear, has cracked. And that again provides a perfect place for bacteria to harbour and form a biofilm and be impossible to clean. This is a wall-to-floor junction where one of those panels has previously been damaged and obviously replaced, but replaced badly so that it doesn't seal either to the wall or the floor and allows for water, food and bacteria to accumulate behind it and again be a perfect place for biofilm to form. It's also difficult to access because of the guardrail that's in front of that, so the hygiene operative will find it quite difficult to get in there to clean it. This is a hand dryer, which you may see quite commonly all over the place, not just in the food industry. And we've shown the biofilms that can form in the joins in the bottom of this hand dryer and on the side with a chemical spray. Obviously, you've washed your hands, you've cleaned your hands, you're drying your hands then to go back into food production. But when you're drying them, the air within that hand dryer can move the cells in that biofilm into the airstream and then possibly back onto your hands and lead to, again, possible cross-contamination when you go back into production. This is an easy one. This is just a puncture in a resin floor where water, food and microbes can accumulate and form a biofilm, and then obviously those cells will be released back onto the floor and be moved around by feet all over the place. This one is a control panel where the operatives have used a cover to protect the electronics in the switch. The cover obviously doesn't work very well because water, food and bacteria have got behind that switch, and you can see the sludge, the biofilm that's formed. And when that switch is touched, that button is touched, some of those bacteria may go back onto the hands and then subsequently be spread by those hands around production. And this last one is an example of where a company had been experiencing a long-term persistent issue with listeria. And it wasn't until they had a refurbishment and removed the plastic cladding from a door frame to find this very mature fungal and microbial biofilm in the wood of the door frame. Obviously, wood not being suitable for this wet production environment. So you never know where you'll find these biofilms. Then there's biofilms that you find in cleaning equipment. So this is a connector for a handle to a broom head. And this obviously hasn't been opened for some time, but when it has been, you can see the biofilm that's formed on the handle underneath. You can actually clean this handle quite easily now for the bit you can see, but how do you clean the biofilm that's probably also up inside that green connector? So a bad hygienic design. This one's probably more to do with bad maintenance. So this twin-bladed foam squeegee hasn't been replaced or cleaned in some time, and when you pull the blades apart, you can see the biofilm that's formed within. And we know that cleaning equipment have been identified as a source of contamination previously, both in a study conducted by Camden and in a more recent study where 67% of equipment and utensils in a poultry plant were found to be contaminated with listeria even after cleaning. Now, whether that's down to poor cleaning or poor maintenance or poor hygienic design, we don't know, but it shows that they can be a potential source of that contamination. So what can we do about hygienic design and implementing that in our factories and equipment? Well, EHEG have produced Guideline 44, which is on the hygienic design principles for food factories. And this covers everything to do with the site location and then the construction and placement of all the facilities within that, including things like the doors, the walls, the floors, and the drainage systems. So that's a good go-to reference guide. At Vikan, we have tried to implement the idea of fully moulded within many of our products, and we now have quite a range of products that are one-piece or fully moulded construction. As you can appreciate, making a hygienically designed brush is incredibly difficult. Fundamentally, it goes against all of the hygienic design principles. You take a solid block of plastic and you drill it full of holes. You then fix a load of bristles into it using a metal staple, providing a perfect place for food and bacteria to accumulate and for biofilms to form. So we tried to design something that improved on that, and here we have the fully molded version of a brush which minimizes that gap. The holes drilled in a standard brush can be up to 1 centimeter deep, whereas the gap here is 1 to 2 millimeters, which is still not perfect, but is certainly a huge improvement and will aid the cleaning of this type of brushware. And then we'll go to the maintenance. So quite often I see one of the reasons why biofilms have formed within equipments and facilities is due to poor maintenance. Now, obviously, it's a requirement with all of these global food standards, which call out that there should be cleaning, maintenance, and repair of the facilities, the equipment, and the utensils within them. So that's a very good reason to make sure that you're doing this. The way to do it really is through regular cleaning and inspection and replacement of both facilities and tools. And with regard to cleaning tools, we have produced this white paper to help you determine when and how is the best way to do this. Once they're cleaned, you then need to store them properly so that they then don't become damaged or recontaminated. So you can choose from things like wall brackets or shadow boards to make sure that they're maintained in a fit condition for use. So now I'm going to leave you just with five, I think there's five, top tips for biofilm control. Firstly, understand your biofilm challenge as much as you can, given that there are still stuff we don't know about biofilms. But understand where and how biofilms are formed, why they're such a problem. Always remember, back to basics in terms of biofilm control. I have no problem with you trying any of the novel techniques, but for fundamental control, please try to stick to the basics. Understand the decontamination process, so which parts of the process are critical to ensure that the whole process works effectively. Use methods and equipment that maximize biofilm removal and minimize its spread, and select the right chemicals for the job. And then understand the importance of hygienic design and its application both in the buildings and the equipment that you're using. And then the regular decontamination, inspection, replacement, and maintenance of all of those equipment and facilities in biofilm control. If you want further information about biofilms and their control, we've now established a biofilm hub on our website, which you're very welcome to visit and find out more. And as part of this presentation, I would normally include a practical demonstration, but given that I can't travel to see you all, we've actually converted that demonstration into a movie, so you can go to the movie and have a look for yourself. It's focusing on the different stages of biofilm removal and which ones are, and how it works as an effective method together. Excuse me. And of course, if you'd, oops, so easy. Hopefully you're still with me. Apologies for that slight interlude. Didn't mean to click on my video at all. Hopefully we'll continue now. So if there are any questions, please contact me. I'm very happy to answer any of your questions. And in fact, I will be here to answer any of your questions now, but if you want to contact me after the webinar, please do so. Thank you very much for your attention. And if you have any questions now, I'd be very happy to answer them. Okay, I've just got to figure out how I can get to this. The question is, will the PowerPoint be sent out for our reference? As far as I'm aware, yes, it will be. I think a recording of the presentation and the slides will be sent to you all after the webinar. Thank you for the nice feedback. Are there ways to detect biofilms? Yes, there are. There are many different ways to detect biofilms. If you want to go down the microbial route, then you obviously do a swab, which you then can send off, and you can have just a total viable count done on that swab, or you can look for specific organisms, maybe pathogens, if that's what you're interested in. Nowadays, you can also have that swab analysed for the genetic makeup of those bacteria. So that's an exciting new aspect of microbial biofilm discovery. You can use rapid detection techniques. So you can use things like ATP swabbing or protein swabbing, which will give you an indication of the level of contamination on the surface, including biofilms. And you can also use these chemical sprays. There's the one that we used for highlighting the microbial biofilm on the hand dryer was one such spray. And they can visualize the biofilm by producing a foam or a color change. So actually there are many different options available to you. Okay, one of the questions here is probably a bit beyond my scope, but I'll come to it anyway. Are there any sanitation chemicals that have a better kill rate on the biofilms than others? I think this is something that you'd need to speak to your chemical supplier about, but chlorine-based chemicals and peracetic acid ones I know are highly effective. The peracetic acid ones seem to be able to break up the biofilms really well. So those are the ones that I know that are particularly useful, but I would again recommend you to speak to your chemical supplier and ask them for more details. So aside from back to basics, what are the other hygiene monitoring control measures the industry can consider? Well, one of the fundamentals of this really is to control water and control time. So if you can, biofilms don't really exist in dry food processing environments because they do need that water to form. As I said, 98 to 99% of a biofilm is made up of water. So if they don't have water, they really can't go anywhere. So to try and keep your production area as dry as possible is really a key factor to trying to minimize biofilm formation and biofilm spread. In addition to some of the other techniques I talked about, the novel techniques like the enzymic formulations or electrolyzed water, UV has been used in the water treatment plants for years. UV is very effective at controlling the formation of biofilm long term. So it's not good on a mature biofilm, but it will certainly slow down, if not inhibit, the formation of a biofilm if it's applied constantly to a surface. Is it possible for a biofilm to be visible but inactive? For instance, black mold staining a floor that has been regularly and aggressively hit with manual scrubbing and appropriate chemicals on a wet factory floor, painted. If the biofilm is not active, it's not really a biofilm anymore. A biofilm is composed of a viable bacteria that will then go on to cross-contaminate and infect. What you'll be seeing with the fungal contamination there is possibly spores, but it is really more to do with staining. So the spores will remain trapped within the flooring material until the conditions are favourable for that spore to become viable again as a viable organism, which won't happen if you keep your regular and aggressively cleaning and scrubbing the floors with chemicals in the food factory environment. It's only if that doesn't happen that then you might have a problem, that the spores might become viable again and cause you an ongoing problem. What would be some key indicators that you are dealing with a biofilm in terms of routine environmental monitoring? If you're doing routine environment monitoring, then any increase over and above what you've established as your normal level of bacteria in that environment would be an indicator that you've got a biofilm forming. So if you're doing your regular, it's all about when you're doing your monitoring, not just looking at the result in isolation, but looking at trends within that. So you'll plot the different readings that you get from your monitoring results, and you'll look for a trend. And if you start to see an increasing level of viable count or ATP result in your monitoring swabs, say that would indicate to me that you've got the start of a biofilm formation. So then you need to implement your cleaning regimes. Can there be very specific microbes according to food types? Yes, there can. There has been research to show that different food types can influence the microbial population of the biofilm. So if you have a dairy environment, especially if it's a chilled environment, then listeria can be predominant in that microbial makeup. And there are other micronutrients within foods that can also influence the microbial population. Has it been proven more effective to use brushes for dry cleaning prior to foaming or scrubbing during foaming? There have been some studies to show that if you employ mechanical action in the way of scrubbing, in addition to foaming, that it will improve the cleaning. So yes, there are some studies available. They are fairly limited. I think most of them would probably, that I'm aware of, would be available from Camden. We're dealing with cleaning drains. Excuse me, is foaming an effective way to reduce the biofilm? If the foaming is done regularly, possibly, but personally, I mean, the drains and biofilms go together like hand in glove. So if a biofilm is going to form anywhere, it's going to form in a drain because it has everything it needs. It has the water and the food and the bacteria. Everything is washed from the environment down into that drain. So biofilms in a drain can actually form relatively quickly and possibly could form to a point where they're resistant to foaming between the foaming periods. So the only concern if you start to use a brush is about the spread of the contamination through flicking. So if you did use a brush in addition to the foaming, then it should be used in an appropriate way by a trained member of staff. So it depends on the time between the foaming and the risk associated with the production area that you're cleaning in. Is an ATP meter a good tester for cleaning and sanitizing determination? I think that ATP is a good indicator of general hygiene. So if you sample a surface in the right way, using the ATP swab in the right way, it will give you a good idea of how dirty a surface is. What it won't do is tell you whether there are any pathogenic organisms there, which could be of concern, especially if there's something like Listeria or E. coli. It depends what you're trying to control. If you're trying to control those pathogens, then you'll also need to back that swabbing up with swabbing for those pathogens specifically. And unfortunately, the ATP test is not always conducted appropriately by the people who do it. You really do need to understand the way it works and to swab a defined area in a defined way so that you can compare the results again as part of your trend analysis. So I think ATP is a very good method, but you just have to use it the best way, and it does have limitations if you're trying to find out how many bacteria or what type of bacteria are on your surface. Are there any cleaning chemicals that you recommend for reduction of biofilm? Again, it would be to speak to your chemical supplier because that will depend very much on your food environment and what you're trying to clean. But as I say, the ones that are fairly, that I know that are slightly better at removing biofilms are the peracetic acid and the chlorine-based ones. But again, I stress, please speak to your chemical supplier. In my experience, what is the most effective method to eliminate biofilms in equipment located in dry factories? Oh, effective method to eliminate biofilms. The most effective method is the one that I've described today. That is regular and effective cleaning and disinfection, whether that be through use of foaming, through scrubbing, or through CIP. It really depends on which food production situation you're in. As I said in the presentation, manual cleaning is the one that's most commonly used, and manual cleaning will be used even when foaming is used and even when CIP is used. So I suppose manual cleaning is the key to them all. In equipment located in dry food factories, I say generally we don't see biofilms in dry food factory environments, but please, if you'd like to follow up on that, please drop me an email and we can go into more detail. Can this information also be applied in the wine industry? Absolutely. Wine and brewing are two industries where biofilms are of key concern. So on an industrial scale, they will use CIP to control biofilm formation. But for the brewery level or the hospitality sector, then these principles can equally be applied. Does the biofilm hold microorganisms? Yes, it does. That's the whole point really with biofilms. They act as a fantastic home for biofilms, a protective home for biofilms. So it kind of, yeah, it acts as a perfect home for microorganisms. Do you recommend rotating sanitizer? Yes, I would do that anyway, not just for biofilms, but for general microbial control in a food factory. There is always a concern about the development of resistance to chemicals by the various microorganisms in the environment, and by cycling between different disinfectants, you can minimize that risk. Gosh, there's a lot of questions. How effective are steam cleaners? Very good. Steam cleaning is another good method that can be used. Again, it's more of well, actually in this case, it depends how high the pressure of the steam is that's applied. The steam can be both a cleaning and a disinfection method combined. You have to be a little bit careful if you're dealing with proteinaceous foods, because the heat can cook the food onto the protein food onto the surface. So it can be an issue there, but it's very good if you're dealing with things like chocolate, for instance. So high fat products that are actually quite difficult to remove, or where you might want to use minimal water to remove that product. So steam cleaning is effective for both food and biofilm removal. I work in a water bottling industry, and I clean the floors and drains in different areas of the production. Can mold affect biofilm growth and spread? Yes, it can. Molds can also make up part of the biofilm makeup. So the population of the microbial population of the biofilm can include molds. So in the same way that any other microorganism within a biofilm can be spread, so can the molds. Is dry ice cleaning better compared with steam cleaning? I wouldn't say it was better. There are pros and cons of both. The dry ice cleaning that I've seen used and tested is quite noisy, but is highly effective. But one has to ask ourselves, where does the contamination go to when the ice crystals remove it from the surface, and is it inactivated when that happens? So I think, again, if you're going to look at dry ice as a cleaning method, there needs to be a risk assessment done as to how appropriate that is for your particular challenge within your food industry. In terms of actually removing biofilms, I'm sure it will be effective, but you need to consider what happens to the cells within that biofilm when that cleaning action takes place. you could find that it spreads the contamination over quite a large distance. Okay, I think that brings us to the end of the questions, and we come to the end of our session. Thank you very much for a very interactive question session. I really appreciate it. And if any of you would like to speak to me further about any of the things we've come across today, or have any further questions, please don't hesitate to contact me. Thank you once again, and have a great afternoon, evening, or morning wherever you are in the world.